Something you can do if a Malamute-Hogarth spacetime exists is run a program, which you don't know if it's going to halt or not. And in this universe, in a Minkowski universe, purely, you would not be able to tell if your Turing machine is going to halt. But it said that you could take a laptop, send it to some point in an MH spacetime, and you'll be able to receive whether the laptop halts or not. So, but then there's issues of quote unquote blue shifted photons. So, what is a blue shifted photon? Is it actually a problem?
Yeah. The blue shift happens because, well, so you're absolutely right in your characterization. What a Malamute-Hogarth spacetime is you identify a point, an event in the spacetime, and you look at its past light cone, and in the past light cone you have an observer with an infinite future that's contained in your past light cone. So for you, you're making an observation at a particular finite point in space and time, but part of what you're observing is an infinite future of some other observer. And so that other observer could be a computer running some kind of program or something. What happens with the infinite blue shift situation is when the computer is sending signals back to that point, they can start to bunch up. And so the signals can get very unreliable, and they can also become very close together. So the wavelength will go towards the blue side of things. And so some people have said, well, this really isn't physically reasonable because of blue shift situations like that. And I think I agree with that. What I've tried to do in some of my work has been to collect up a bunch of reasons that people want to exclude these things for. So blue shift would be one of them. Another one would be, whether the standard energy conditions are satisfied. Another would be, well, we don't want to have this computer having to accelerate really, wildly, and have, infinite fuel to traverse whatever world line it's supposed to traverse. So you can collect up a bunch of these things, and what I do is I say, look, here's a model. I go to work, in my little workshop, building a little model, and the model is a Malamute-Hogarth spacetime that has none of those unphysical properties, right? The irony is that this model is pretty unphysical.
Even by your standards.
Even by my standards, yeah. So there's an old technique introduced by Penrose, and Garrosh used it a lot in his work. Hawking used it with Ellis in his textbook. You might term it the cut and paste construction. It's where you take models of spacetime, like relatively, well-behaved models, like something like a Minkowski spacetime, and what you're going to do is you're going to cut slits here, and you're going to, glue things together, this to this, and you're going to create wildly crazy topologies in this way. They're going to be standard models of GR. They're going to count as models of GR, but they're going to be wildly unphysical. Now, those folks, Penrose, Garrosh, others, they emphasized early on that the point of these examples was not to show, it wasn't to exhibit a physically reasonable model of our universe, but rather, if you're studying something like logic or something like this, counterexamples are just so important. And so they serve the purpose of being counterexamples to certain lines of reasoning, right? And so in this case, I would say, the example that I'm coming up with that's very unphysical is a counterexample to a certain line of reasoning that goes like this. Malamute-Hogarth spacetimes can't possibly happen. Why? Because they have unphysical property X, Y, Z. I'm going to say, well, I have a counterexample to that line of reasoning because I've now exhibited a spacetime, which is Malamute-Hogarth, that doesn't have property X, Y, or Z. And so what it does is it puts the ball in the other person's court again and says, if there's something else you're thinking of that makes it unphysical, then speak up, come up with some other criticism here, but the criticisms you have so far aren't quite enough.
Hawk-eared or the analogy for hawk-eyed, but for listeners, the eagle-eared. I'm not sure. Listener may have noticed that you use the term obtain. So people who study philosophy are distinguished by their use of the word obtain. Physicists who haven't studied philosophy never use the word obtain.
Really? Okay.
So obtain just means that something becomes the case.
Yeah.
I want to know, you mentioned earlier that there's a difference between not only the way that Malamud does the philosophy of physics compared to other philosophers of physics, but you also mentioned that there's a difference between the way philosophy of physics is done and philosophy per se as such. So what is that difference?
Well, I think one thing to say is that philosophy of physics even is a very diverse thing. So there's all sorts of styles of philosophy of physics. You've encountered some of philosophers of physics, right? You had David Wallace on your program, Tim Maudlin, I think. So you're familiar with. I mean, both of those folks have very different style than I do. I'm in a style which is on the more mathematical, logical, rigorous side of things, I would say. The way I attack a problem is to try to formalize that problem and come up with a proof or a counterexample for a given philosophical claim. But if you look at the work of other philosophers, it's going to be very different. They're going to not necessarily be so rigorous. They're going to, here's an example. This is not my field at all, but something like quantum field theory. There's going to be some philosophers of physics who want to really make that into a really rigorous type thing. That's difficult. And so what they might do is they might go to an algebraic approach to that, maybe look at C-star algebras or something like that. Whereas, someone like David Wallace or others, they might, want to dive into the practice of how folks are trying to make sense of quantum field theory within a physics department or something like that. So these styles can clash, and these clashes can pop up at a conference. There are more styles than that too. I mean, there's styles where it's very disconnected from the actual practice of physics, where you're looking at something like time travel you're starting in a different place. You might bring in physics here or there, but you're not starting with, okay, let's assume we're working within the context of GR and let's ask this question. Rather, you're saying, I'm not going to, start from GR, where I'm going to start from my own, I've got my own system. And so there's a lot of different ways to do philosophy, and looking back on my own trajectory, when I was a youngster, I just wasn't aware of all of these ways. I mean, for me, it was just like there's physics, there's philosophy, bringing them together. That's got to be like this one thing, but it's not one
right.
thing.
There are a couple levels here. So number one, when you tell people you go into math, if you tell lay people who haven't studied any math, they may think that what a mathematician does is something like an accountant, where you're multiplying just larger and larger numbers together, and maybe something like the Pythagorean theorem. And they don't realize that it's much more than that. And then when you realize that it's much more than that, you don't think in terms of there are styles to that much more than that.
Yeah.
That Grothendieck style is different than Terry Tao's style. And something that didn't occur to me is that there are different styles of philosophy of physics until just speaking with you now and thinking about it. So is there a style of philosophy of physics that you envy, that you think, oh, I wish I could do that?
Yeah, I mean, I certainly envy. David sort of invented this style of doing philosophy of physics, and so
Which David?
David Malamud. I would say, yeah, I'm very envious. I try in my own way to work in his style. I have my own style, though. My style is one where I don't put a sentence in a paper. I don't put a word in a paper unless it's necessary. And so my papers can be 2-3 pages. That's very unusual in philosophy. It's maybe more common in physics, although that's even pretty short for physics. But I like to let the results speak for themselves. I mean, I think a lot of philosophers, what they'll want to do is they might have a result. Most philosophers don't prove theorems, right? So they're not actually making progress on the mathematical, physical side of things. What they're going to do is they're going to take existing statements and they're going to philosophize about them in some way, right? For me, my theorem, that is my philosophy. And so I let the results speak for themselves, and I try not to add on top of the results some flowery prose about whatever, or what the meaning of this is or something. I just the result is what it is. That's the philosophy.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high quality podcast. Something else you should know about is that if you go to their app, they not only have daily articles, but they also have long form podcasts with their editors and writers. This is also available online. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.